Hello, hello, hello. Good morning.
Good morning.
Morning. Hey, Professor Younger, did you get my email last week?
I remember getting a couple emails from you. Let me see. Let me double check just to make sure we're talking about the same thing here. I think I did, and I thought I even replied.
No, you never did.
No, and I don't see my reply either. So okay. Give me an idea what it was pertaining to, and
It's it's about that zodiacal chart.
oh, gotcha.
I tried to do it on Microsoft Word, but I don't think it's working out. Would it be easier if I just sketch it out and put the photo on Microsoft Word?
Yeah, that's fine. If you want to do that, you can draw it.
Thank you.
Yeah, no problem at all. Sorry I didn't catch your email. So
App,
yeah, everybody, if y'all are having problems with the technology, I mean, I'm not supposed to be grading you on your technology skills. So if you can't figure out how to put it up there with Word or whatever, then by all means, draw it, take a photo of it. Ideally, if you have the right tools, you can save that photo as a PDF and you just turn it in that way. Because I don't actually need the lab turned in this particular lab. All I really need is the actual zodiacal diagram with the Earth orbit, with dates, and with the sun in the center.
by the way, I already turned in my moon project last week.
Yep, I did see that. So we're golden on that one.
Uh-huh.
Oh, there you are. Yeah, I see you emailed me on 113. Oh, I see my reply. It was evidently it was never sent. Okay. Well, at least I found your email, so that makes me feel a little better.
Yeah.
So, anybody else have any questions? Remember, your lab's not technically due till Thursday, anyways. But do remember that also your classes, unless you're literally taking a class on Microsoft or something like that, your classes at TCC are not supposed to be about the technology. I mean, if you're taking a computer science class or a Microsoft Word class or Excel, then yeah, they're very much about the technology. But if you're taking something like physics or astronomy or chemistry or biology, then if you're having technical difficulties with the actual software of Word or something like that, then contact your instructor and they're probably a workaround.
I see chapters 13 and 14 will be the last.
13, 14, and possibly we usually jump to maybe 20. I think it's 24. It might be
It
21. I can't
it
remember
is
the last
24.
chapter. Yeah. So that's life, basically. That's the chapter on life. So I try to cover that when I have time. Now, I should have enough time. In fact, I'm only going to do, a chapter a week. So today we're doing 13. And then next time, or next week, we'll do 14. That'll be week 14. And then the following week, we'll do 21. On Thursday of this week, we'll do something related to this chapter or watch something or something along those lines. Okay.
I think I'm going to get another C on chapters 9 through 10, but I can live with that.
Gotcha. Well, I just posted test, I guess it's test five.
Yeah, you
Uh,
did.
okay. And
Chapter
test 11 or test six will be up as well. So this one's going to be due a week from today, or actually a week from last night at midnight. So it should be due on the 19th at 11:59 p.m. I will probably go ahead and put up practice test six today. If not, it'll be first thing tomorrow. And that one will probably be due. I'll actually put up the actual test probably Thursday, and you'll have until the following Thursday to get that one done. Just because we got a little bit behind on our test because I completely just forgot to give you a test. So this one's on 9 and 10. The next one will be 11 and 12, and the next one will be 13. Did you say the last chapters were 13 and 14? Is that what I remember you just saying?
Yeah, I did, but
But
I
24
think
was
I
also.
yeah, I believe yes, I did say that. Chapters 13 and 14.
Yeah, so that's the deal with that. now's the time where you got to start looking for, oh, no, that's right. I just remembered that we're doing Respondus. So if you guys can't do your Respondus monitor and Respondus browser, now's the time to start looking for your ability to schedule a proctored test. So make sure y'all do that if you're having any difficulties with Respondus, because our final exam is a face-to-face test in some sense. So, and I will probably allow you guys to do it. I'm probably going to allow you guys to do it on the first and Tuesday of the last week instead of having to wait till Thursday. And in fact, I might even make up a second version in case anyone wants to take it early. Okay. All right. Well, I guess, does anyone have any other questions before we get started? So notice the test is up there. I have started putting the due dates on Canvas. So Canvas should remind you, hey, you got a test due today. So make sure you log into Canvas every day just to make sure you don't miss any assignments. Your homeworks are available, of course. You still got a little bit of time left for Astro Points. Whatever the date was in the syllabus, I want to say it's the end of April. That's the due date for all the Astro Points. It might be a little earlier or a little later. I'm not sure. Sorry about that. But make sure you get those done on time. Astro Points are extremely important. Remember, you only have to have a minimum number. Once you have that minimum number, then nothing bad happens to you. But once you have that next number, which is 2,500 points, 2,500 points. Once you get that 2,500, then I add 3 points to your course average. If you get to the 3,000, I add 5. If you get to 3,500, I add 7. So that's what Astro Points are about. A bare minimum, you got to have 1,500 to make sure you don't lose 10 points on your course average. And once you have that, you're free. And if you're good, if you're happy with the way you've been doing in your tests, including your midterm and your finals, then you don't need any more Astro Points in the 1,500. You just need to make sure you don't lose any, like by not doing a moon project or something like that. So with that being said, and looks like no one else has questions, I'm going to go ahead and jump to sharing my screen for the PowerPoint for Chapter 13. Chapter 13 is kind of a fun chapter. It's actually where it's the first chapter that 242 covers, or excuse me, 140, dang it, the second semester of astronomy covers. All the numbers are running together in my head, so I just punted and said astronomy. Yeah, astronomy 132. That's the one I was going for. So that's the first chapter where astronomy 131, 132 deviate from one another. So it's actually a pretty straightforward chapter. Oh, geez, why can't I stop yawning this morning? It's terrible. So in this chapter, chapter 13, we're going to learn basically about how we measure the various stars, and then, in other words, measure the distance to them. And then we're going to learn about what we've discovered about the various stars. In other words, ranges of masses, ranges of temperatures, ranges of luminosities, which remember is the total amount of radiation put out by the star. So on a light bulb, that's the 100-watt figure on a light bulb. That's the luminosity of the light bulb. And it's a little different in a light bulb because a luminosity of a light bulb, say being 100 watts, really means the total radiation put out. But that's not really the same thing as what you might expect, because 100 watts of light being put out by an incandescent bulb, not a fluorescent bulb, only about anywhere from 5 to 20% of that is actually put to visible light. The rest of it's actually pure heat. We're doing sort of the same thing when we're calculating the radiation put out by a star. We're calculating the radiation put out, in other words, the number of joules per second over all the various wavelengths. So it sort of is like that, but at the same time, I don't want you to get confused and think that that's the whole amount of visible light that a 100-watt light bulb is putting out. So the learning goals for chapter 13 are: 1, explain how astronomers use brightness of nearby stars and their distance from Earth to determine how luminous they are. In other words, what's the relationship between luminosity and brightness? Learning goal 2, explain how astronomers obtain the temperature, sizes, and composition of stars. So that's the Stephon Boltzmann Law, as well as some other things that we can make use of. Learning goal 3 is describe how astronomers estimate the masses of stars. That's basically with binaries, or perhaps if you find a star with something orbiting it, you can use it to determine the mass of the star. Learning goal 4, classify stars and organize that information on a Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is a monumental achievement, and it makes us or gives us ability to do a lot of things that we didn't think we could do rather easily. So once you realize a star is a main sequence star, as opposed to some of these dying formations of stars, then you can immediately put it on the Hertzsprung-Russell diagram just by knowing either its luminosity or its temperature. Normally, you know its temperature. That's the easiest thing to come up with. Once you have that on the Hertzsprung-Russell diagram, then you can figure out its luminosity, and then you can use the luminosity to figure out how far away it is. So it's a really wonderful tool. There's other things it can do as well. And then finally, learning goal 5, explain how the mass and composition of a main sequence star determines its luminosity, temperature, and size. So that's the 5 learning goals for chapter 13, the chapter on taking the measure of the stars. Let me go ahead and start in the very first or the very second slide, which is one of the coolest photos ever. So here it is. Oop, I got another person entering. Hold on. So this is really one of the coolest photos ever. So this is Orion. Hopefully everybody recognizes that by now. You can actually see in this photo some really cool stuff. For starters, you see a little thing going on over here. That's in fact another nebula. You can see all this red going over here. That's in fact a nebula. That's all this nebula. So when I repeatedly tell you that the constellation Orion is kind of special, in that the brightest stars we see for the constellation Orion are all formed from the same nebular cloud, you can see now, oh, wait a second, this nebular cloud's the same size as Orion. Look how big that sucker is. Now, the main parts you look at are either in his scabbard, where his sword would be held. Notice this is his belt. This is his back shoulder. This is called Betelgeuse. This is his front shoulder. This is his back foot. This is his front foot, called Rigel. You can see some pretty nebula material right here, and that's the Great Orion Nebula. But you'll also know there's another nebula over here that you can see. All of it's more or less part of the same thing, and they're different areas where star formation is going on. And another cool thing about this, remember what the definition of a modern definition of a constellation is. A modern definition of a constellation is a patch on the celestial sphere that has some weird shape that encloses basically the original constellation, but it's everything in that patch. So you can see in this photograph how many stars there truly are, and every star you see here, assuming the line for the border of Orion doesn't go like right here, in which case you have to cut out these stars, but every one of these little stars you see are really in the constellation Orion. And then we of course start naming them. Alpha for the brightest, which is wrong, but is still called Alpha Orionis for Betelgeuse, and then Beta for the second brightest, which is Rigel. Again, that one's also errant, but we kept the alpha beta descriptions for historical reasons. And then Gamma, Delta, and then they go through other naming procedures for naming them based on brightness and stuff like that. They go through the Greek alphabet, they go through numbers with alphabets, all sorts of cool stuff. So one of the neat things you can immediately tell from this points us to the Stephon Boltzmann Law. And the Stephon Boltzmann Law, remember, is the luminosity is equal to a couple of constants multiplied by each other times the surface area times the temperature to the fourth power. So what that means is there's two ways for a star to get bright. You can either make it bigger by increasing its surface area, or, well, I say to get bright, to get luminous. Let me use the proper words here. There's two ways you can make a star more luminous. You can either increase its surface area, which means increase its radius, and that luminosity is proportional to radius squared, because surface area is 4 pi squared for a sphere, and for an ellipsoid, it's a similar type formula. So it's always proportional to the square of the radius. And the other way is by increasing the star's temperature, and in that case, the Stephon Boltzmann Law goes like temperature to the fourth power. So the fact that originally the ancients thought that this star was brighter, and later when modern technology came along, we found out that this star is actually technically brighter, that should tell you something. That should tell you that these two stars have very close or very similar luminosities. Okay. Now, that actually should just tell you that they have very close brightnesses. But if you combine that with the fact that I just told you that all the bright stars in Orion all came from the same nebula, then the closest star of the brightest ones in Orion and the farthest star of the brightest ones in Orion are much closer to each other distance wise than they are away from us. So that tells you these stars are all about the same distance away. Now, brightness is really how bright it appears here at Earth. So you can have something that's super, super bright, but if it's 13 billion light years away, you're not going to be able to see it very well at all. Or you could have something very, very dim and have it, 4 light years away, in which case it would appear very, very bright. So there is a relationship between brightness and luminosity, and that is the brightness is equal to the luminosity divided by 4 pi r squared, where r is the distance away. Okay. So when you're comparing brightnesses for something that has the same distance to them, then you're comparing luminosities as well. So now that I know Rigel and Orion, and Betelgeuse and Orion are both about the same distance away, when I compare the brightness of one of these to the brightness of one of the other ones, then I'm really just comparing the luminosities. So that tells me something. Luminosity, which remember I told you depends on the r squared because it's surface area, and the temperature to the fourth due to the Stephon Boltzmann law. Since these luminosities are about the same for Rigel and Betelgeuse, then that means their luminosity is about the same. But how can we possibly make that happen? We know that Veen's law says that basically the longer wavelength has the lower temperature and the shorter wavelength has the higher temperature. So what we see here is a blue star, Rigel, that's got to be super, super hot. And then Betelgeuse, which is a red giant, supergiant actually, is a reddish star. So that must be super, super cold. In other words, this is on the order of 3,000 or 4,000 Kelvin. This is on the order of tens of thousands of Kelvin. So according to the Stephon Boltzmann law, since temperature is raised to the fourth power in the Stephon Boltzmann law, a temperature of 10,000 versus 4,000 is literally 2.5 times higher temperature. So if you take 2.5 and you raise that to the fourth power, you see that's a lot different in luminosity. 2.5 to the fourth power is a huge number. Well, it's 5 halves, so you can say 5 times 5 is 25, times 5 is 125, times 5 again is 625, and then over to 16. So 625 divided by 16 times more luminous is what you expect Rigel to be over Betelgeuse, just from the temperature. But they're about the same luminosity, therefore the Betelgeuse star must be compensating for that factor of 625 divided by 16 by an r squared. So if you take 625 divided by 16 and you take the square root of that, then you know how much bigger in radius Betelgeuse must be than Rigel. And in fact, you figure out that Betelgeuse is so big, it will almost certainly engulf the orbit of the Earth and maybe even the orbit of Mars if we were to replace our sun with it. So that's the instructive part about the Orion Nebula. Literally the first or second day of class when we learned about stars and brightnesses and how we name stars in constellations, we said the brightest star in a constellation is called Alpha, followed by the nominative version of the constellation's name. So this would be Alpha Orionis, Betelgeuse would be. And then the second brightest star would be Beta Orionis. And then, of course, I pointed out that, in fact, it's opposite, but we got to keep that name just for historical reasons. So that's what I like about this diagram, in addition to showing you where you can look with, and I'm talking looking with binoculars. If you take and look at this area with binoculars, you will see pretty gassy color stuff. Same thing over here as well. You will see pretty gassy and color stuff that is a nebula. and you don't need a fancy telescope. Like literally binoculars will work. Also over here. So that's one thing that's really awesome about the photo. And the other thing is the big teaching moment where you can really make sense of the Stephon Boltzmann law and how luminosity is related to not only temperature, but in fact, surface area. Any questions on that? Now, in case this lecture doesn't do that well for you, you'll notice that I've already posted in week 13 a lecture for chapter 13 as well from a previous semester. So you can check that out too. But anyways, this is the lecture. Let's carry on. So how do we study the stars? Well, what is the actual brightness of stars? So that's one of the things we try to do when we're studying stars, is find out what the brightness is. And the brightness is an easy thing. Remember, brightness is really how it appears bright to us. So it's sort of like counting the number of photons that hit our CCD, our charge coupled device, our camera, in other words. So we have a camera and it has a certain number of pixels, and basically anything, say for instance Betelgeuse, sends out a spherical distribution of light equally in every direction. Now, on the surface area of that giant sphere, okay, that giant sphere that's centered on Betelgeuse, picture this in your head, we get a little patch on the surface area of that sphere. And the area of that patch is the surface area of either our retina, where our eye is looking at it, or our camera, our CCD device, or whatever. That's the little patch that we get. So that's why brightness is really the luminosity divided by 4 pi r squared, because we're taking the luminosity, which is all the radiation put out over that entire sphere, and dividing it by the surface area of that square of that sphere, so that we get joules, which is energy per time, or excuse me, watts, which is energy per second, divided by square meters. So when we multiply that by the square meters of our CCD, that's the actual brightness. So the brightness is actually how many photons and what their energy is falling on the little CCD camera or the retina of your eye or whatever. How do we learn anything about the stars when all we can do is collect light? Well, that's amazing, because thanks to modern physics, specifically what we now call astrophysics, we know all these neat laws. We know about the Stephon Boltzmann Law that tells us, for instance, how the luminosity is related to the radius of the star and the temperature of the star. We know Veen's law is related to the peak wavelength. In other words, when you make that Planck type curve that Planck derived the formula for, that is really energy output versus wavelength, that there's a peak on that curve, and the wavelength at which that peak occurs is indicative of the temperature of the actual object. So that allows us to determine temperature. So that's wonderful. That's how we can actually tell 2 things already. We've figured out basically the temperature of the star, the surface area of the star, the brightness of the star, the luminosity. So several things have been figured out. And then we can take that same light and spread it out over a spectrum like that Planck curve does, and see what colors are missing and what colors are present. And that tells us what elements are present and what elements are not present. We can look at the Doppler shift of those individual spectra, the lines in that spectrum. And the Doppler shift tells us how rapidly the star is moving to us and how rapidly it's moving away from us. And we can tell which one it's doing. And then we go to the next area is, how do we classify these stars? So what we'll find out is there's a couple different ways. There's O Be a Fine Girl, Kiss Me, which is ultimately turned out to be the temperatures of the stars, O stars being the hottest and M stars being the coldest. And then finally, what are the determining factors of luminosity, temperature, and size? All that will make sense of in this chapter. Any questions on any of that? So astronomers measure stellar distance, brightness, and luminosity. That's among the many things they measure. And remember, distance is what they're calling stellar distance, is really the distance away from us to the star. The brightness is how bright it appears to us. And that is, by the way, directly related to the magnitude. So remember when we talked about first magnitude star being the brightest, second magnitude star being the second brightest, and down to the sixth magnitude. It actually goes way further than that, but six is about the best you can see with human eyesight at the most perfect dark spot ever. Okay, if your eyesight's bad, you probably can't see a six, and if you're in an area like downtown Virginia Beach, you probably can't see any better than a four, maybe even a three. Okay, but the main thing to remember about that isn't the mathematics of how brightness is related to luminosity and all that stuff. Even though your book covers that, and a lot of courses take time to make sure you know how to do that, this course doesn't. The most important thing for you guys to remember is that you can tell me at the drop of a hat whether a one star, whether a one star is brighter or dimmer than a two star. Hopefully y'all can do that, right? Which one's brighter, a one star or a two star? Anyone?
One star?
Exactly. Yeah. Yeah. It's supposed to be really that easy. So I just want to make sure y'all were still there. So yeah, that's the main thing you need to know about brightness. There's relative brightness, which is what we normally use, but there's also absolute brightness, which can be mathematically related to luminosity, and that can be one of the things we plot on the vertical axis of a Hertzsprung-Russell diagram as well. And then there's, of course, the luminosity, which is really the total radiation put out by the star. The luminosity is measured in watts. That's joules per second. And remember, a joule is about as much energy as it takes to lift a good-sized red delicious apple off of the floor, lift it up, and put it on top of a kitchen table. That is about a joule of energy. And a watt is a joule per second. So a 100-watt light bulb, for instance, is taking enough energy every second to lift 100 red delicious apples off the ground and put them on the table. And that's what you're getting per second for a 100-watt light bulb. So that gives you some idea of what these fields are. But that's what the luminosity is, the total energy output. The brightness, on the other hand, I'm not talking about magnitude, because that's some mathematical crap we made up to make sure that it had nice even whole numbers and stuff like that. But the brightness, on the other hand, is really measured in watts per square meter. So we're taking that luminosity and dividing it over the surface area of a sphere centered on that star, and whose radius is the distance from that star to us. Okay, so that's where the units come in and all that stuff. It is necessary to understand mathematics and the physics of light in order to understand stars. Obviously, that's the case. I don't make you do much of the math, but I do need you to understand the concepts. So one of the first ways, or one of the easiest, most straightforward, direct ways of measuring distance is called parallax. And it turns out there's this, what we call a distance ladder, that we use in astronomy. And basically, if you're going up to 10 to the negative third or 10 to the negative 2, maybe, parsecs, which, remember, a parsec's about 3.26 light years. So if you're going well under a parsec, if you're staying within our solar system, we can immediately measure the distance between Earth and other objects using radar. We can literally just send a beam of radar light, or even laser light, if you saw the episode of The Big Bang Theory, and it can bounce off the moon, off a mirror that, in fact, we left on the moon specifically for this purpose. We can bounce it off that mirror, have that beam of light come back, and we calculate or measure how long it takes the beam from the time we sent it to the time it returned, and use that to determine how far away it is. That can be done, like I said, throughout most of the solar system. Maybe not to Pluto, and maybe not to Neptune at different times, but basically we can get all those distances with radar. Then we realized that if you hold a pencil fairly close to your nose, but out in front of your head, okay, and you open your right eye, the pencil appears to be on the far left of the background. Now, when you close your right eye and open your left eye, the pencil now appears to be on the far right of the background. And if we push that pencil, instead of being close to our nose like the red one is in this diagram, if we do that with the blue pencil and we put it further out, then what we realize is the movement from right eye to left eye for the more distant thing is going to be smaller. using that and basic trigonometry, we can figure out how far something is away from us. Now, what we did is instead of using our eyeballs, which are not very good, but that is why we have, stereoscopic vision. That's why we have 3D vision, is because we have two eyeballs. Having two eyes is a convenient thing, and it lets us have good depth perception. That's also the reason that after, dang it, I can't remember the NASCAR racer, he got in that really horrible wreck and lost one of his eyes. His son races too, or his son might even be about their age to retire now. But anyways, he lost his eye, and it was a long time before they let him race again, specifically because of depth perception. So without two eyes, you don't have much depth perception. It's a really hard thing to do. And obviously depth perception when you're driving 250 miles per hour next to a wall, it's probably helpful to have some decent depth perception. When we did this though, we decided to define a unit of distance called the parsec. And basically, anytime a star is 1 parsec away from us, so we imagine instead of left eyeball and right eyeball, we imagine the Earth in January and then the Earth in July, say. Okay, so the Earth in January would be on one side of the moon, of the sun, and then the Earth in July would be on the opposite side of the sun. So the distance across there is in fact 2 astronomical units. Now, if you look off to a very distant object, and this angle, not the whole angle, but half of this angle right here is 1 arc second, then the distance to that star is called a parsec, for parallax second. So literally, if we're looking across from the Earth in January to the Earth in July, this distance is 2 astronomical units. And if this angle right here is, this whole angle is 2 arc seconds, and the half angle, of course, is 1 arc second, then this star is exactly 1 parsec away, which we've since discovered. And you can do this mathematically if you wanted to, but you're not required to, because that's not what this class is about for me. Then when you do that, you'll find out that this distance is about 3.26 light years. So anytime a thing is 1 parsec away, we expect to get a measurement of 1 arc second compared January and July. If, on the other hand, you find that the arc seconds is even smaller than 1 arc second, then that would suggest that the star is even further away than a parsec. And in fact, the formula is straightforward. 1 over the angular measure in arc seconds is equal to the distance in parsecs, and 1 over the distance in parsecs is equal to the angle in arc seconds. So it's a very straightforward formula. It's one of the few formulas I require you guys to do. Let me stop for a second and show you that. So what we're talking here is looking at my document cam instead of the top of my balding head. Stop your laughing, Tyler. Okay. If you see the distance and we measure that in parsecs, which is a PC, that is actually equal to 1 over the angle, which we measure in arc seconds. So I'll put a little dash mark there. Okay. That happens to be the same thing as parallax in arc seconds is equal to 1 over distance in parsecs. So if I tell you, for instance, that the parallax angle is 4 arc seconds, then you can immediately tell me the distance is what? How many parsecs?
One-fourth.
1/4. And that's the best answer, right? Because you don't even have to use a calculator to do that. Now, if you happen to remember that $0.25 is a quarter, then you also know that 0.25 parsecs. Okay, so it's 1/4 parsec, and this is actually a unit that goes up there, not down here at the bottom. But anyways, yeah, that's it. Now, if I tell you that a distance we measured in parsecs was in fact, let's say 100 parsecs, then the parallax angle we measured in arc seconds would be what? And use Amy's famous way of doing it where you don't have to waste time doing long division. I think
1 over 100.
exactly 1 over 100, and that's arc seconds. And of course, everybody should know that that's 0.01 arc seconds, because this is the tenths place, this is the hundredths place. So yeah, that's basically it. So this is a formula that I do expect you to be able to use. And all you got to do is whichever one I'm giving you, and I'm not going to give it to you in the wrong units and make you convert from light years to parsecs, or from arc seconds, or from degrees to arc seconds, even though I could. I'm not going to do that. So all you have to do is do 1 divided by whatever I give you, and that will give you the other one. Does that make sense to everyone?
Yeah.
So a distance of in parsecs equal to 1 parsec implies a parallax angle measured in arc seconds of 1 arc second. Okay, that's it. That's the crux of that formula. So I just want to make sure you guys followed that. And like I said, this is one of the few areas where I actually do require you to do that particular math, and that's mainly because it's so simple. Okay. And the more important thing is that the parallax angle, as it goes up, obviously the distance goes down. So they're thumbs up, thumbs down. And that's the concept that you should take away from it. And not only should you have the concept, but you should be able to do the math as well, as I just showed you. Any questions on that as we cruise along in the hot?
Show me the 100 thing again.
Okay, if you do 1 divided by 100, let me do this real quick.
No, cancel the share screen. I just need that sheet.
Okay.
No.
Yeah,
Okay.
this is an arc second over here, so it's supposed to be 2 little quote marks, if you will. And it's 1 over 100. And then remember your places in the decimal. This is 1/10. This is 1/100th. The next one would be 1/1000th, so on and so forth. So if you have 1/100th, if you want to write that as a decimal, you just put 1 in the hundredths place.
Got that.
Some old school math that's a pain in the butt, which I don't know that that's what Tyler was asking about, but anyways. So back to our slide again. And if we take 2 days to do this, that's okay too. I still have some other stuff we can work on. Let's see if I can get this full screen. So again, that's our second way. Now, the beauty of the ladder, remember I was telling you about this ladder, and you can measure distances with radar up to, almost as far away as Neptune and Pluto. Maybe even if we're really, really careful, we could possibly do Neptune and Pluto using the right things. But once we start doing our parallax, we can double check that with the radar because there's an overlap. Obviously, you can use parallax to calculate things that are even closer to us than, say, Pluto or Neptune. And when you get a confirmation of those distances matching the distances you got in radar, then you're more confident about your ability to use the parallax angle. And that's a good thing, right? And those two are really our only, quote unquote, direct way without having knowledge of the star of finding the distance. But using that ladder, now that we have that direct way with the parsec, whatever way we find next, wherever it overlaps the parsec method and how far it can see, we can use the parsec to verify that method. Once we have verified that numerous times, then we know that new method is reliable. And then we can find another method that overlaps that last one. And then we can find another method that overlaps the next last one, and so on and so forth. And that gets us further and further away. Does everybody understand what I'm saying about this ladder, this distance ladder? Anybody have any questions about that? I can't remember if they actually show the distance ladder in chapter 13. I know they do later in chapter 19. And they really should show it in chapter 13, but I don't think they do.
Can you briefly explain it one more time?
Yeah, okay. Let me do it with this way. In fact, let me show you with something more visual. Okay. What I'm going to do is open my Microsoft PowerPoint, and I'm going to open the slideshow from chapter 19. And that's right here. And now I'm going to share my screen. with that new PowerPoint up. So now I'll do share screen. Here's a new PowerPoint. Okay, this is chapter 19. I'm going to scroll on this side till I see the ladder. There it is. So this is our distance ladder. Notice this measurement along the top are in parsecs, PC. So the radar can get us to about 10 to the negative third. Parsecs are about 1/1000th of a parsec, which would be basically 0.003 light years. So on the order of several astronomical units. So the radar, just sending a beam of light or a radar, which is a radio wave, sending it out and letting it bounce off of something and then return, we can use that to get most of our solar system. Then we can use parallax to measure anything all the way up to about 10 to the fourth or 10,000 parsecs, which, remember, a parsec is 3.26 light years. So we're talking basically 32,000 parsecs away, or excuse me, 32,000 light years away is what we can use parallax for. So parallax has that overlap with radar. That's why we could use radar to verify that our parallax method was working. And that's just straight geometry. So there's no reason to suspect it shouldn't. But we always have to test these things. Now, once we get beyond that, we can use what's called spectroscopic parallax. And when you use spectroscopic parallax, you can now start to say, okay, well, there's an overlap between parallax and spectroscopic parallax. And while that overlap is happening, you can use this to verify that your technique, which I haven't talked about yet, spectroscopic parallax, is working. And that gives you a great deal of confidence in spectroscopic parallax working, which works well beyond 1 million parsecs. So we're talking 3 million light years, and in fact, almost to 30 million light years, because this would be 10 million right here. So we're basically, or I shouldn't say 30 million. This is 1 million. So we're at 3 million, and this is 10 million, and we're about halfway to that. So that'd be 5 million parsecs is about as far as we can go, or 5 million light years is about as far as we can go with spectroscopic parallax. Then beyond that, we can use Cepheid variables, which I've mentioned several times before, but basically there's a star in Cepheus, Delta Cephei, whose brightness does this. It makes a sine wave. So basically its brightness gets a peak brightness, then it gets a minimal brightness down here, then it gets a midline brightness and a peak brightness again, and then keeps on doing that. And if you measure the time between peak brightness and peak brightness, there's a formula that relates that time period to the actual brightness of the star. And when you find one of those stars, as Hubble did in the Andromeda Galaxy, then you can use that as a standard candle. So if you find a nearby galaxy, which might be, 1 million parsecs away, you can first use spectroscopic parallax to find its distance. Then you can use the Cepheid variable to find its distance. And if those two agree, then you're more confident about your Cepheid variable knowledge. And now that Cepheid variable knowledge allows us to go to 10 million, even 100 million parsecs, which again is about 320 million light years. Once we get beyond that, then we can start using type 1a supernova, which has this neat little characteristic curve where the brightness from a supernova comes off and then falls down and then plateaus and then falls down again. We know when that type of supernova occurs, which is really basically matter falling on a companion star until it got so much matter that it had to explode and basically create like a helium flash. When we do that, now we can get all the way to 10 to the 10th. Excuse me, 10 to the 10th, even 10 to the close to 10 to the 11th parsecs, which is on the order of 100 million light years. Okay, so that's the distance ladder we're talking about, and the overlaps is what help us. We even get so far as saying, well, if I look really far away at all the star clusters, say open clusters and closed clusters and stuff like that, all those different clusters of stars, And the biggest one we've ever seen in any direction is, let's say, 25 light years across. Then we even start using things like, okay, well, I see a star cluster, and the biggest it could be based on our own statistics is 25 light years. Let's assume that star cluster is 25 light years. How far away must it be for it to be 25 light years and be that small in our telescope? We can even use that. But notice, just like with the Cepheid variables, the spectroscopic parallax, and the supernova, those things require us to have some knowledge of the objects that we're looking at. It's not just straight geometry anymore, but because it has the overlap with the previous things, we can use that. So they literally use stuff like that. Oh, the biggest, star cluster we ever saw was 25 light years across. Ergo, we can sort of, as a first order approximation, assume that none of them are going to be any bigger. Let's assume, therefore, that each one we see is 25 light years across, and then use that to find the distance to other things. Okay. Any questions on that now? I think that's a pretty good explanation of the distance ladder. What you ultimately see, though, is even going beyond, you can then use what Hubble found if you're actually measuring galaxies, or at least measuring distance to things in a particular galaxy. Then you can use Hubble's law, and Hubble found that basically the velocity that something leaves from you with is directly proportional to how far away it is. So if you find the redshift of a particular galaxy is such and such, you multiply that redshift in such a way that you get the velocity, then you divide that velocity of redshift by the Hubble constant, and that'll give you the distance away. And that gets us out to millions of light years, in fact, tens and even hundreds of millions of light years further away. Of course, hundreds of billions of light years doesn't work, but we can even get on the order of hundreds of millions. So, all right. And it sounded like I did hear some confirmation that that was somewhat understood. So share screen back to our slideshow, which is this beautiful thing. So that's the stereoscopic vision, that's the parallax, and that allows you some deeper knowledge, I think, now that you've heard the distance ladder. That gives you some deeper knowledge of how we measure distances. This is them actually not only sort of working out the math with this diagram at the top, but down here, this is what the photos would actually look like. So these yellow stars that you see around here are really, really far away compared to star A and star B. And the reason why we know that is look how close this star is to this side and this side. And notice even over here, it's the same distance. So that must be super far away, so far away that we can't use parallax to measure it. So all those yellow stars are background stars and are clearly further away than A and B. And it's not always that they're perfectly left and right of each other like star A and star B are. Star A, in going from, let's say, January to July, star A could actually move this way to this way, or it could move this way to this way. And star B, of course, will move the exact same way that star A does. But the main thing is when you measure the actual distance across, that's twice the parallax angle. When you're using, for instance, a telescope, you know what the focal length is. And from that focal length formula, you can use that to figure out exactly how many arc seconds is in a photograph, width of a photo. So if you then say, okay, well, this is from here to here is 10 arc seconds across, which is really awesome for a telescope. Okay, that's like Hubble level. And this seems to take about 80% of that. So this must be 8 arc seconds. That's literally how you do it. You can take a tape measure or take a ruler, measure from the left side to the right side, set that centimeters equal to the number of arc seconds that the photo is wide, and then measure in centimeters again from the center of this star A to the center of star A in this later appearance. And when you do that, which by the way is just right ascensions and declinations, when you do that in centimeters and divide that centimeter by the number of centimeters that the photo was, you'll get a measurement in arc seconds that you just multiply by the arc seconds of the photo. Okay. Again, that's getting in the weeds of telling you how to go about doing it, and that's something I'm not making you do, but I wanted you to understand it's really just straight proportions. There's no fancy calculus or not even any algebra to doing this stuff. So that's how the parallax works. It's the only direct way to measure the distance to a star, other than, like I said, radar, and even radar requires us to, assume that light is traveling at the speed of light in a vacuum over the area it is, and there's some chance that it's going to hit something other than a vacuum, but it's still it's very accurate. Let's put it that way. So, and an arc second, by the way, remember there's 60 arc minutes in a degree, just like there's 30 minutes in an hour. And then there's 30 arc seconds in each arc minute, just like there's 60. Why do I keep saying 30? There's 60 arc seconds in every arc minute, just like there's 60 seconds in every minute. Okay. So ultimately a degree is 3,600 arc seconds. That's the number I expect you to know. Okay. I expect you to know 60, 60, and then 60 times 60 is 3,600. So distance, brightness, and luminosity. Now, once you have the distance to a star, then you can take the brightness, which is literally like counting photons and the energy of each photon that hits your camera. So that's something, brightness is something that we can easily measure. All we have to have is equipment, right? And long as we're here on Earth and we can see the thing, we can get brightness. Once we have brightness, if we then have the distance, then we can use this formula. I'm going to stop sharing for a second. We can use this formula to figure out the actual luminosity. So brightness, which is measured in watts per square meter, is actually equal to luminosity, which is measured in watts, divided by 4 pi times the distance squared. And this is the distance between the object measuring the brightness and the actual object with whose luminosity you're determining. Okay, that's the brightness luminosity relationship, which we can write with symbols a lot easier. Brightness is equal to luminosity over 4 pi times the distance squared. And that's all because, remember, when a star or something is actually putting out light, it puts out an equal amount in each direction, right? So if we take a sphere of radius d, and then we take the luminosity, which is really a total number of watts, and we divide it by that little area, or in this case, the whole area of 4 pi d squared, then we're getting the brightness. We're getting how much of that falls on our little camera or whatever. And then, of course, we also know that luminosity, according to Stephon Boltzmann Law, is the emissivity constant times the Stephon Boltzmann constant times 4 pi r squared times t to the 4th. This is really the surface area of the star, which a lot of stars, probably most stars, are spherical, but some stars actually can spin so fast that they're not really spherical, they're more ellipsoidal. But either way, they're still dependent on r squared. So you can see, hey, once I have the brightness, which is easy to measure, and I have the distance, then I can clearly just solve for luminosity, because luminosity would be brightness times 4 pi d squared. Now, once I have the luminosity, if I use Veen's law, and Veen's law, of course, says that the temperature is equal to, I think it's 2.9 times 10 to the -6 Kelvin times meters or something like that. And I'm just going to put a question mark over that because I can't remember which number. I know it's 2.9 something, divided by the lambda, the wavelength of the peak. Okay. So this actually gives you the temperature. All you have to do is plot the graph that would look like this, and that's lambda peak. So once you make that plot, you now have the temperature. And since you know the brightness and the distance, you found the luminosity. So you got now luminosity and temperature. That allows you to determine the radius of the star. So see how those things all come together at once? And by the way, this isn't necessarily the best way to find the temperature, but it is a way, okay? The best way is looking at the actual curve, which doesn't look like this. The actual curve looks like more like that. And each one of those dips is an absorption spectra. And what you can find out is whichever lines are the most intense. So if they're emission spectra, they would be the brightest of the bright. If they're absorption spectra, they would be the blackest of the black. Either way, the most intense ones are the ones that are in a very specific temperature range. It turns out, for instance, that hydrogen has a very specific range of temperatures where you can see those lines very prominently. So if you see that the hydrogen lines are really intense, then you know the temperature range is between those two temperatures. But then you say, oh, wait a second, there's a carbon line that also has a very specific range of temperature, and those lines are very intense, but that range of temperatures is right here. So since both of those are intense, now you know the temperature range is somewhere between these two instead of all that. So you've narrowed the temperature down even further. And then you find there's in fact another element that has intense lines, and its temperature range is like right here. So now you've narrowed the temperature down to that little bit. So that turns out to be the best way to determine temperature. We can get it nearly down to within a few Kelvin of one another. So that's the best way, but this is a way. The main thing is once we have temperature and luminosity, we can then determine the radius of the star. Okay, does that make sense to everyone? So it's a multi-step problem here, figuring out how all these things are. And I don't require you to do all this math, but I need you to understand as a college student, multi-step problems are your forte. That's supposed to be, what a college educated person can pull off. Either explaining the multi-step process or actually doing it with the math. In this case, I'm not requiring you to do it with the math. I just need you to know, hey, brightness is something we can always measure. And if we either have the luminosity, we can find the distance. But if we have the distance, we can find the luminosity. Only one equation means you only get to solve for one variable. This has 3 variables in it, and you can only solve for one, right? Same thing here. This has 3 variables in it, and you can only solve for one. Now, if you put these two together, then you can solve for 2 different ones. And if you put these 3 together, then you can solve for 3 different ones. But the main thing is one equation means one unknown that you can solve for. 2 equations mean 2 unknowns that you can solve for. 3 equations mean 3 unknowns that you can solve for. But the main thing is each time you have one of these formulas, if you get all but one of the things, you can automatically get the last thing. Okay? So I'm going to go back to sharing the screen, which is this one. So one star may appear fainter than the other. That star is truly less luminous, or is it because it's way farther away? That's always a problem. So if you're looking at 2 stars and you see one is really dim and one is really bright, that could be that this one's really less luminous and this one's super luminous. Or you could be looking at things that are really far apart, and this one is quite luminous, but it's also close. This one could, in fact, be way more luminous than that one, but because it's so much farther away, it looks less bright. Okay, so that's the big deal with that. So brightness is the rate at which we receive the energy and depends on the observer's perspective. The brightness depends on both luminosity and distance. A dim star could have a low luminosity or be far away. A bright star could be close or have a high luminosity. And there's the formula that I just gave you. I gave it to you, solved for brightness. So I said brightness is equal to luminosity over 4 pi times the distance squared. They're giving it to you the other way. Doesn't matter. I'm not going to make you use that formula either way. But since you see that brightness is 1 over the distance squared, I can tell you, hey, if a star has a certain brightness, what will its brightness be if I double the distance away? Then you should tell me, well, the brightness should be decreased by a factor of 4. Everybody understand that? That's just like gravity. Gravity was Gmm over r squared. this is L over D squared. So this acts just like gravity. If I double the distance away for a star, then its brightness goes down by a factor of 4. If I triple it, it's going to go down by a factor of 9. If I quadruple it, it's going to go down by a factor of 16. If I quintuple it, it's going to go by 25. If I hundredtuple it, then it's going to go down by a factor of 10,000. Everybody understand what I just said there about the dropping? That is, in my world, that's not math. Okay, that's the concept. So I do expect you to be able to answer questions like that. Hey, a star has a brightness of 80 watts per square meter. If I move it twice as far away, what will its brightness be? Well, if I move it twice as far away, it's going to decrease by a factor of 4. So instead of 80 watts per square meter, now it's going to be 20 watts per square meter. That's a fair question that I do not consider mathematics. Everybody get that? Anybody need any extra explanation on that? All right, moving on. So when we actually go out and look at stars, this is sort of what we find out. We find that the relative number of stars whose stellar luminosity is 10 to the negative 4th as luminous as the sun, 1/10,000th the luminosity of the sun. That is, in fact, on the order of 5 out of, let's say, 100 stars that we look at. 5 would probably be, actually, I should say out of 1 million. Yeah, so this graph is really just showing, hey, there's really large numbers of luminosities, or excuse me, of stars between 10 to the negative 4th and 10 to the negative 2 solar luminosities. They are, in fact, a large number, but as you get more and more luminous, the number of stars that we've seen of those higher luminosity goes down further and further and further. So the most luminous stars go all the way up. In other words, we don't find any more luminous than roughly 1 million solar lumens. So we're saying 1 million times brighter than our sun, excluding the distance. Right? So notice how easy it is to accidentally say brightness when you mean luminosity. When I say that in this scenario, I'm trying to consider them as if they're all the same distance away, in which case you're talking about the absolute brightness, which is, again, another measure of the luminosity. So our survey of the stars tell us, one, that the vast majority of stars are less luminous than our sun, okay? And the further you get away higher than the luminosity of the sun, the more drastically they are less of them. So this might be, for instance, 5 hundredths of the stars that we find would be 100 solar lumens or more, right? And then as you get further and further along, you see they decrease. So this is the kind of thing when we look at the star coming, or the brightness coming from a particular galaxy, and we actually correct for how far away that galaxy is, then we're seeing in the luminosity of the galaxy, we can use this line to estimate what fraction of those stars in that galaxy are 1 solar lumen, 2 solar lumens, 10 to the negative 3 solar lumens. And that actually allows us statistically to calculate roughly how many stars we expect to see in there. Again, based on the total brightness as well as the total mass of it. So that kind of data of percentages versus actual stars, that's really helpful for us to estimate number of stars as opposed to just the total star mass in a galaxy or something. So we can learn about the temperature, size, and composition of stars by looking at the light they emit. There it is, 2.9 times 10 to the negative 6 is what I said, but they got nanometers. That'd be 10 to the negative 9 times 10 to the 6. 10 okay, so my expression should have been 10 to the negative 3rd, not negative 6, when I wrote the stuff, or excuse me, the Veen's law. So Veen's law says temperature is equal to 2.900 times 10 to the 6, and that's nanometers times Kelvin per lambda peak. Again, this is an equation you don't need to be able to use mathematically, but I do need you to realize that since T and lambda peak are on opposite sides of the equals and opposite sides of the fraction bar, they're thumbs up, or thumbs up, thumbs down? Anyone?
Is it thumbs up, thumbs up?
No, it's thumbs up, thumbs down, because whenever they're on opposite in both things, they're on opposite sides of the equal and opposite sides of the fraction bar, then they're opposite. One thumbs up and the other thumbs down. If the lambda was up here next to the Kelvin, then it'd be thumbs up, thumbs up. Okay. So you need to know, and I expect you to know, that large wavelength means low temperature and low wavelength means large temperature. So lambda peak is the wavelength at which a star is brightest. Again, this is a way to give us a very specific temperature. This is the way that when you go to, for instance, a doctor appointment now, or even into a school building or something, they check your temperature by either shooting something, aiming something at your forehead, or literally touching your forehead, or literally just quickly sticking something in your ear. It makes a beep and they pull it right out. All of those are done using Veen's law. So what they're doing is they're taking that device that they aimed at your forehead, or they aimed in your ear, or they put against your forehead, and that's making that curve like Planck had defined, and it calculates basically what wavelength that peak occurs, and then out using this formula spits a temperature. And then of course they've got corrections for it because they've done, you know, actual analysis of humans, and they find that a human's forehead temperature is this, is normally indicative that their core temperature is this, so they make corrections for that. But that's really how those devices work, is with Veen's law. So looking at the peak color gives us the star's temperature. Again, that peak can be outside of the visible spectrum, in which case it's really just the highest part that's in the visible spectrum tells us the color. Let me stop on that one again and remind you what that means. So we can have, for instance, the peak curve can look like this, and it's always one side steep, and that's the low wavelength side. So wavelength is going up as you go this way, and this is the energy output. Okay, this is lambda peak. Now, if we happen to have Roy G. Biv, remember this is in order of increasing wavelength, so this is Viv Gior. Now, that would suggest this star is green. Now, if we had another graph for another star, and in fact, it looked like this, okay, and we had the visible spectrum right here, Vib Gior, then notice this peak is outside of the visible spectrum, but the star will appear red. And then finally, the last scenario would be this, and this is Vib Gior, in which case this star is going to appear blue. But notice again, the peak is not in the visible spectrum, so we can't, oh, I wrote that too low. We can't use the peak to call that a color, because clearly that's out beyond the ultraviolet. It's at least in the ultraviolet, but it might even be beyond ultraviolet in the X-rays or even the gamma rays. Okay, so that's really how the star color is affected. It's always the part of the curve that's highest from violet all the way up to, and this should be lambda peak. Let me make sure y'all know that. That's the actual end. So from violet all the way to red, wherever the curve is highest in between these, that's the color it'll appear. In this case, it appeared on green to be the highest, so it's a green star. On this case, it appeared outside of visible spectrum, but the highest part was at the violet end, so you'd say that's a blue star. And at this point, the highest was at the red end of the visible spectrum, so this star would appear red. Does that make sense to everyone? Anybody have any questions on that? Okay, so let's go back to our sharing. So that's what Veen's law gives us. Obviously, we can initially just look at the color and we say, oh, that's a blue star or white star. Well, that must be freaking hot. Okay, that's the first thing you're going to know. And then when you actually do the analysis, you can get that the peak might actually be outside of the visible spectrum. And that's okay. It's not a deal breaker. That's still the truth, and that still works. So this is what the Planck curve is supposed to look like, right? According to Planck's equation that he derived and won a Nobel Prize for. And obviously this peak occurs right here in the green. So this would be a green star. And this is very much like the spectrum of our sun. Our sun actually has a peak that's pretty much in the green part of the spectrum. It's just our eyes are not good at seeing green. Again, that's another essay you guys can write for Astro Points if you so desire. But when you see the actual spectra, that's the total light coming out from the core. But as the light leaves the core of the star, it goes through a less dense, cooler atmosphere. And that less dense, cooler atmosphere, according to Kirchhoff's laws, will actually create an absorption spectra, because various elements, compounds and whatnot in that atmosphere are going to steal the photons that match energy differences between its electron orbits. So if it sees this particular wavelength right here, if it takes that wavelength and you say H times C over that wavelength, and you get an energy that matches E2 minus E1 or E3 minus E2 or E12 minus E11, if that matches for one of your elements, then that sucker's going to be gone. Okay, it's going to absorb that photon, or at least some fraction of them, and it'll leave a hole or a dark line in the absorption spectra representing that particular transition of that particular element. If, on the other hand, it was an emission spectra like what you get from an excited nebula near a bunch of stars that were just created, then you have essentially the envelope of the same curve, but you only have spikes trying to fill in that. So this spike, for instance, might have been representing this particular part of the curve, and then all these other spikes are the shorter parts. Okay. But again, those individual spikes correspond to energy differences. And since it's a spike, that means photons were emitted at that particular wavelength. If you take that HC and divide it by the wavelength, then you'll get an energy, and that energy must have matched the energy difference between two orbital levels of the electrons for either a element or a compound.
3 minutes left.
Thank you, sir. Does everybody understand how I'm using that spectra to make sense of the elements present? We've already covered this before, but I want to make sure you guys understand. So the spectrum is the amount of light emitted as a function of wavelength. Here's various spectrums, or spectra, plural. So it turned out with anti-jump cannon and Edward Pickering's harem, as it was called, it's kind of disparagingly, that was a bunch of women during World War I who basically he recruited, because one day he was being a punk, as PhD advisors often are to their to their graduate students. He said, my housekeeper could do a better job at analyzing these spectra than you do. And he took it up a notch. You know, he wasn't just a jerk that would say that mean thing to a grad student that, you know, thinks that guy hung the moon. He's also the guy that went the next step, and he brought his housekeeper, who happened to be a woman that we now know as Annie Jump Cannon. She turned out to be a friggin' ringer. And because of that, she ended up classifying over 200,000 stars during her life. She could literally just look at a spectrum and immediately tell her it's an O5 star or B0. Well, when those women were working on the stars and the spectra, they didn't really know what the spectra meant. They didn't know what the lines meant necessarily. Later on, another woman of the group that actually came from Great Britain, Cecilia Payne, she actually comes along and figures out what that is. And in fact, writes a thesis, a PhD thesis that could have won her a Nobel Prize. But in the very end, she was talked down by not Pickering, but another guy who said, there's no way in hell you're seeing hydrogen in all those stars. Hydrogen is not that prevalent in the universe. So she said, but clearly I'm wrong, and literally like put that as the last line of her dissertation. And to her credit, she said that's her fault. It's not his. You know, she shouldn't have listened to authority. She should have went with her gut. But in this process, they were putting together, you know, the stars with these types of line, they called A. The star with these types of line, they called B. Stars with these, they called C, and then D. And they basically used, you know, a lot of different letters of the alphabet. But when Cecilia Payne comes along and figures out what these lines mean, it turned out they didn't need all those letters, and those letters, other letters, were not that useful. The only letters they really needed was O, B, A, F, G, K, and M. O, be a fine girl, kiss me. O, be a fine guy, kiss me. Whatever you want to do for the mnemonic is fine. And those actually represent temperatures, and they further subdivided it to O0 being the brightest of the O stars, down to O9 being the least bright of the O stars, and then B0 being the brightest of the B stars, down to B9 being the dimmest of the B stars, or excuse me, the coldest of the, I shouldn't say brightest, I should be saying temperatures. So the highest temperatures are
10:45.
O0. Thank you. The highest are O0, and the coldest of the hot are O9s. So I do expect you to know that classification. O, be a fine girl, kiss me. O is the hottest, M is the coldest, and O5 is colder than O2, for instance. R stun, by the way, is a G2, and it's a G2 V star, which actually means its main sequence. So that's some of the classifications we're getting to. That's plenty for today. I didn't complete the chapter, and that's okay, because I'll cover the rest of it next time, and that works out just fine, because we'll do 13 this week, we'll do 14 next week, and then we'll jump to 24 the week after, and the week after that will be a final. So you guys are done. You're free to go. Make sure you do your test. Okay, you got a test due a week from last night, so make sure you get that done. But everybody's free to go. I'll wait for the last one to leave in case anybody has any questions.
Professor Younger, just making
Right.
sure. You said I can sketch out the zodiacal chart, right?
Yes.
Okay.
Just turn it in as a
Bye.
PDF. That's all I care about.
I will. Later.
See you, man.
Hey, Mr. Younger. I just wanted to talk to you. I'll be able to make it to the lab because I'm actually going into firefighting, and I have to take a physical on that day.
Mm-hmm. No problem. It's
So I
not a
just want to
big
let you know
deal.
I might not be able to make it to that lab.
I will post it. I'll post it at least by that day, what we're doing. So you can just look in the website, find out what we did. And I usually post a video if it's very relevant. The last couple haven't been very relevant. That's why I haven't. But if you have any questions about what's to be done, just, email me, ask another student, call another student, email another student, whatever you want. And that'll be fine. So it's not a big deal. You missed one day of attendance. That's not a big deal.
Okay, cool. All right. Thank you.
All right, see you, Jamie. Good luck on your testing or whatever you're doing.
Appreciate it. Thank you very much. Have a good one.
You too.
Mr. Younger, can I
Yes.
talk to you after everyone leaves?
Yes. Does anybody else have any questions? If anybody's got private ones, I can take you to the breakout room and leave everybody out here. So does anyone have any other comments or questions before go to the breakout room with Matthew? Amy, you good?
I'm good.
Okay. And Amanda's good too? All right. I will do a breakout room. I'm going to do one. And I am going to assign this room to Matthew, and I will meet you there, Matthew.
Okay.
See you, Mr.
and-
Younger.
What's that, Amy?
I'm gonna head out. I have a physics test to study for.
Oh, awesome. Go kick butt. Who's your physics teacher?
I got Ippolito.
Oh, okay. Well, good luck on that. I know he's not easy, but he tries.
He does try.
Well, and also, if you ever have any questions about that, you can ask me too. That's, I'm the department head, so I can certainly help you if you have any questions.
All right, I will.
All right. See you, Amy.
See you.
Bye, Amanda. I'm going to go to breakout room 1. I don't think Amanda's even here, so. I went to do join, duh.
What happened? What just happened? Mr. Younger? Hello? Mr. Younger? Where?